Hello, we're Group 10. I am Brandon Tran, and with me are my group mates Tyler Vong and Larry Tran, and today we're presenting our final project, Optimizing Transaction Concurrency Control on Postgres for High Concurrency Workloads. Outline. Here's a quick roadmap of our presentation. We'll start by describing the problem we aim to solve, move into our project's goals and the challenges faced, then review some key related research. After that, we'll go into our implementation, including an early attempt, our final solution, and how it works under the hood. Finally, we'll share the results, discuss what we learned, and outline future directions. The problem statement. To kick things off, let's look at the core problem. Postgres uses multi-version concurrency control, or MVCC, to manage concurrent access. While MVCC enables non-blocking transactions, it runs into issues at high concurrency, like deadlocks, high CPU usage, and rigid locking behavior. This becomes especially problematic in diverse workloads where a static strategy doesn't adapt well. That's why we set out to explore how Postgres could better manage high concurrency environments through a more dynamic and adaptive approach to concurrency control. Goals. Our main goal is to keep Postgres ACID guarantees intact, meaning every transaction should remain atomic, consistent, isolated, and durable while improving performance. We also aim to reduce latency, increase throughput, ensure fairness by avoiding transaction starvation, and build a solution that adapts automatically to changing workload patterns. Challenges. As with any systems level project, we ran into some major challenges. We had to deep dive into how Postgres handles concurrency, which meant learning its C-based source code and understanding how its internal file structure is organized. Another big challenge was scaling our benchmark tools, especially HammerDB, to simulate over 100 virtual users without resource limits getting in the way. Related work. Before jumping into our solution, we grounded our work in several key pieces of existing research. Sadogi, in their paper Reducing Database Locking Contention Through Multi-Version Concurrency, demonstrated that MVCC is effective in reducing locking contention. However, they also pointed out that static MVCC implementations struggle to adapt under changing transactional workloads. Guo, an adaptive optimistic concurrency control for heterogeneous workloads, proposed a model that dynamically switches between optimistic and pessimistic concurrency strategies based on contention levels. While their approach is flexible, it wasn't specifically designed to handle Postgres's MVCC overheads, such as tuple versioning and garbage collection. Usui, through their work, adaptive locks, combining transactions and locks for efficient concurrency, introduced a mechanism that switches between traditional locking and transactional memory depending on runtime contention. Although designed for programming environments, the underlying concept of dynamic adaptability strongly influenced our design. Finally, Zhao in their paper, An Adaptive Strategy Integrating Locking with Optimistic Concurrency Control, proposed a hybrid concurrency control model that intelligently transitions between locking and optimistic execution. While their results were more theoretical, we extend their philosophy by directly embedding dynamic locking behavior into Postgres' MVCC layer. Together, these works informed our hybrid adaptive MVCC system, which translates these theoretical insights into a practical solution. Early implementation. Before landing on our final design, we first tried a more targeted fix by modifying the LW, which is a lightweight lock acquire function, in LW lock.c. The idea was this: if there was an exclusively locked request and waiters were already present, we'd set a release flag early to free the lock sooner. This would avoid unnecessary delays at the end of long-running functions like for loops. Unfortunately, in practice, this didn't make much of a performance difference, but it gives us key insights that helped inform our more adaptive approach.
After evaluating different approaches, we settled on a hybrid adaptive MVCC model based on our related work that combines two key ideas. Smart lock downgrading. This lets transactions start with a strong lock and dynamically downgrades to a weaker one, like key share, if conditions allow it. Adaptive feedback mechanism. This adjusts behavior like sleep times in the locking process, depending on the system load. At the core is our high contention function. It checks whether the number of active backends exceeds 60% of the system limit. If so, we apply stronger locks. If not, we favor weaker locks to increase concurrency. To guide this adaptivity, we introduce a way to measure contention levels with this theoretical formula. where A equals the number of active backends, M is the maximum allowed backends, W average is the average wait time, T average is the average transaction time, and if C exceeds 0.6, we classify the system as being under high contention and adjust the lock strength. This model gives us quantitative basis for our lock decisions in real time. This slide shows the architectural changes of Postgres SQL for our system. First, we have a lock strength controller to decide how strong a lock should be. Then we have a contention monitor that constantly checks the system load, and an adaptive scheduler that coordinates the transactions based on those insights. To implement this, we use the Windows subsystem for Linux with Ubuntu. We compiled Postgres SQL from source, then modified the files like heap am.c and proc array. We benchmarked our changes using two tools, pgbench for light workloads and hammerdb for OLTP style TPC workloads that really stress the concurrency. These code snippets show how our logic plays out. First, everything is tracked using hash bucket. Then the function is high contention determines if the system is under high contention based off the number of active backends. Depending on that result, we either apply a strong lock tuple exclusive or downgrade to a lock tuple share. This decision making happens in real time during the transaction's execution, being adaptable without requiring manual tuning.
All right. So moving on to our benchmarking and results, we use pgbench, which simulates basic TPC-B workloads, and hammerdb, which runs a more complex TPC OLTP benchmark. And we measure TPS, latency, and standard deviation. So after running our results, the first result is the modified with our implementation, and the second result is the base Postgres source code. As you can see, that our results resulted in higher TPS while also having lower standard deviation and lower average latency. So, moving on to our conclusion. So while we experience better results based on our benchmarks, we still experience inconsistencies like occasional dips in TPS, high standard deviation, and latencies every now and then. These issues could be because of contention tracking overhead, retry logic delays, and other inaccuracies with our implementation. When benchmarking, we ran our tests under default configurations, and further tuning could result in better consistency. Additionally, our work does not cover all dimensions of concurrency control, such as snapshot management, and the implementations could be more refined to make sure it works for all situations. Different scenarios, such as read-heavy, could have been tested to make sure it scales perfectly, as these logics could add more unnecessary overhead. For our future work, we should benchmark on more powerful computers, such as supercomputers, OUGPEL, AWS, and more. And we should also implement real-world dataset simulations to make sure that it works in real situations. And for future work, we could turn towards hybrid knob tuning along with more code level adaptation. Moving forward, we will now present a live demonstration of both the modified implementation along with the stock implementation for Postgres. here are the references we used for this project.